because the six-membered ring, along with the five, are found very commonly in organic-based compounds, be they drugs, natural products, specialty chemicals. You can learn a lot. We say that the six-membered ring is a wonderful pedagogical tool for learning about flexibility or rigidity of various organic-based structures. I'm using Sci-Gress as a platform, and what I'm going to do is simply open up a folder, pre-existing folder, and I'm going to go to File, New Object. Now, don't worry about this. This is Sci-Gress. I'm simply using this as a convenient platform for illustrating the six-membered ring. Now, don't forget molvieu.org, molvieu.org. You can find an open source platform for building 2- and 3-dimensional structures. And you can also investigate that for examining the six-membered ring, which we call cyclohexane. But anyway, let me get you up and running with this. Now watch. New object, molecule, okay. And then I'm going to draw. All I want to do right now is just get a six-membered ring. 1, 2, 3, 4, 5, 6. Now I'm going to connect them, making single bonds. Each platform you use, ChemOffice, Sci-Gress, each platform will have a little bit different approach to drawing. Now I'm going to select a molecule, and I am going to grab this whole thing, and I'm going to do what's called action beautify. What that does is add hydrogens. Okay, I'm going to drag it over. Now, what you have right now, let's begin our examination. Carbons in gray, hydrogens in white, six-membered ring. I'm going to rotate it. And when I rotate this, I see by default it is building a non-planar six-membered ring. In other words, it's not a hexagon. You have 6 sp3 hybridized tetrahedral carbons, and in order to give them the best possible environment to be in, we go from a planar six-membered ring to a so-called chair, because it looks like a chaise lounge. But notice, one up, one down, one up, one down, one up, one down. Now, it turns out by doing that, you're minimizing torsional strain, eclipsing of vicinal or adjacent lone pairs, one sigma bond eclipsing another in a torsional angle of 0 degrees, dihedral angle 0 degrees, that's torsional strain. You're eliminating steric strain. There's not a lot with hydrogen, but we're able to minimize eclipsing of hydrogens or larger groups by going to the six-membered ring. Now, you do create a situation where the internal angle is about 111 degrees. Ideally, we'd like it 109.5, but 111 is not bad. So we're really minimizing angle strain, torsional strain, steric strain. We are creating 3 so-called axial hydrogens, 3 above, 1, 2, 3, 3 below, 1, 2, 3, and there are 6 in the equator or equatorial. Can you see that one? 1, 2, 3, 4, 5, 6. Now, I want to impress upon you, if you are a beginning student of organic chemistry, that you will be studying reactions, mechanism. A reaction would be the face of a clock. Mechanism would be the components behind the scenes making the clock function. We want to know reactions. We want to know mechanisms. We want to know about rates, thermodynamics, intermediates. All these things you must learn, but you also have to begin to study three-dimensionality, because bioactivity depends very strongly on not only the right functional groups present, but the geometry, the so-called pharmacophore. You want to excel in organic, which is the gateway, what I call introduction to molecular science. And all of the advanced molecular sciences are based on a firm grasp of fundamental organic. You can do a lot with 1 year of organic. And, a big area attracting a lot of bright young minds is synthetic biology. And you want to prepare yourself for the investigation of biochemistry, molecular genetics, molecular physiology, immunology. All these heavy hitting sciences are based on organic chemistry, the fundamental molecular science field. Put the time in with this. It's not difficult, but you're going to start to create mental images when you look at structures of what they may look like in 3D. Easier said than done, but you'll be using a computer down the road to assist you, like what I use. Now, 3 above, 3 below axials. What's bad about that, not so much with hydrogens, but it'll get worse with methyl or T-butyl groups, alkyl groups. You have 1,3 diaxial interactions. 1, 2, 3. 1, 2, 3. 1, 2, 3. You see the triangle? 1, 1, 1. Those are called 1,3 diaxial interactions. Unfortunately, that is a bad thing, but the lesser of the evils versus having a planar 6-membered ring. Now, as your groups get bigger than hydrogen, they're going to start bumping into each other, and that's not a good thing. So you see, you've got 3 above, and then I'm going to flip this around, 3 below. Now, I'll tell you something. When I was an undergraduate, and I'm 67 in June, when I was an undergraduate, we had one set of molecular models for about 100 students. And it was like driving in a whiteout. If you ask anybody in my age group, maybe someone in your family that has studied organic, or if you ask any older professors, it was like driving in a whiteout. We knew there was tremendous potential in organic, but three-dimensionality was lagging because we did not have powerful programs for rendering. Nowadays, you're going to have holograms. You are going to have tremendous means of visualizing structures you're studying, visualizing their degree of flexibility. It all starts here with this ring. Okay, so 3 axials above, 3 below, and 6 equatorials. That's called the chair. Now, is this the only conformation, this chair? Oh, no. No, no, no. You will be studying ring flip. Now, I won't do that right so much now, but there is what's called ring flip, conformational isomerization. You can turn that ring inside out. It does require energy. It's easy to do at room temperature for cyclohexane. At lower temperature, it becomes harder. A rotational barrier or inversion barrier can present a problem at low temperature. But you can turn the ring inside out, and what was axial is now equatorial. And this will turn out to be very important, but we won't do it in this. I just want to show you the flexibility of this ring. Now watch what we're going to do. I'm going to do an experiment up here. Run an experiment. I'll just click OK. And we are going to do conformations, list of minima, and we'll do just molecular mechanics right now. I don't want to get into ab initio and semi-empirical methodologies. I do that in other videos. So let's run it. So we'll start. And then you get this graph in Sci-Gress. Now, let me just run the film. I'll click here. And we're proceeding. Do you see the broken vertical line? We are looking at alternative conformations of the ring. And we're proceeding from low energy to high energy. Now, let me stop right there. Got it. There is your chair. let's go up here. What is this? Well, that's not a chair. You see, there are other conformations. And as you do a ring flip, when you turn a cyclohexane inside out, you have to proceed through higher energy conformations. It's like jumping over a pole vaulting. And in order to turn that ring inside out, you have to go through higher energy conformations. At lower temperature, as I said, that can become very difficult. At room temperature or above, it's easier. And you always want to have large alkyl groups. An extreme would be a T-butyl or a neopentyl group. They're very large space-demanding groups. They want to be placed equatorial because equatorial positions afford much more breathing room. But let's go up here. What's this? Now, we begin to see a high energy conformation. And you see, with this, it's not planar, but we're getting eclipsing of this carbon and the one behind it, this one, the one behind it, the hydrogens are eclipsed. That's a high energy intermediate. You see the value, 17.24 kilocal per mole. Now, there is an equation that allows you to determine the percentages the percentages of one conformer versus another as a function of energy. And you studied that in general chem. Let me go back here. We're getting towards the lower one. See, 10.64. So there's an equation. I'm not going to tell you what it is. You go and find it. But there's an equation where if you know the energy difference between conformers at a given temperature, you can determine the percentages of each at equilibrium, chemical equilibrium. So this is a low energy chair. And the beauty of this is that you can also generate a pool of conformers to investigate because, you know, that cyclohexane may be part of a drug candidate. And you want to know exactly what that cyclohexane conformation is like depending on what's attached to this. Now, if we do another experiment, let's see. I'll X this out. I'm not going to save that for this. X it out. Now we do another experiment, and we can do molecular dynamics. Now let's see if I can find that here for you. Chemical sample, conformations, sequence of conformations. Let's see. Right now, let's do conformations from dynamics, molecular dynamics. And we'll just run molecular mechanics. You're going to get better thermodynamics, heats of formation, like the differences in energy between conformations. That is best done with ab initio calculations or semi-empirical quantum. Molecular mechanics is very good for bond angles and bond lengths and can be used with large molecules like proteins, and it is. But if you're dealing with small molecules, organics, if you want to know more reliable calculations of energy differences, then you're going to carry out other calculations. But for now, let me just show you this molecular dynamics. You start at absolute zero and you go up. And this will run. And to make a long story short, you go from absolute zero, 0K, and you start to put in energy, kinetic energy, potential energy, and you can generate a pool of conformers to study. So for example, let me click on this one. Okay, let me click on that one. This is a way to generate a pool of conformers, and each one can be saved, and each one can be studied by freezing all of the atoms, and you can get measurement of various energy contents. The less energy a conformation has, the more stable. So molecular dynamics, this has been used by physicists since about 1950. It's a very important part of drug design by computer. And nowadays, rarely do you ever design new drugs without using the computer platform first to save time and money. Okay, so you can just go in randomly and get a feel for how flexible a molecule is. Morphine is a very complicated structure, but it's not that flexible. It's actually quite rigid. So flexibility means you have a lot of conformers to investigate, trying to find the one that is bioactive. The lowest energy conformer is called the global minimum, but you can't assume that the bioactive conformation is going to be the global minimum. It may be a few kilocalorie per mole higher than that. So we normally put these conformers into subpopulations, and you may have a cutoff and say, I'm not going to look at anything above 10 kilocal per mole, and then you look at the lower energy populations, and but you can see with molecular dynamics, this is a way to give you a feel for the different possibilities. Okay, I'm all talked out, and if you made it to the end here, bless you, and study your 6-membered brain, learn everything you can about it, because then you're going to be learning, you're going to start to have dreams where you actually see molecules, and in some cases, later in your career, you may see them undergoing conformational isomerizations like ring flip. It's really amazing. All right, bye for now.